The high-energy lifestyle of hummingbirds presents several challenges. Hummingbirds have to ensure a constant supply of energy to fuel their rapid wing beats. But they also have to worry about storing enough energy to make it through a long overnight fast or power a migratory journey. They do this eating nothing but simple sugars in nectar. My name is Ken Welch, and I'm an assistant professor in the Department of Biology here at the University of Toronto Scarborough, and I'm a vertebrate comparative physiologist. And this is Chris Chen. Chris recently completed his master's degree in my lab. We all know that hummingbirds like eating nectar, floral nectar, and really all that is sugar water. And that is the sole source of most of their energy. So we ask the question, what do hummingbirds burn to power their extremely energetic hovering flight? They can fuel basically all of that expensive hovering metabolism with the sugar that they've been drinking just 20 minutes prior. And then we ask the question, well, what about the individual components of that sugar? We know table sugar, sucrose, it's what we add to our cereal or our coffee. That is glucose and fructose. And if anybody's been paying attention to the news, they know that fructose is a bad character. High fructose corn syrup and the prevalence of that in our diet these days is correlated with the rise in obesity in humans. And part of the reason for that is that we're not good at using fructose specifically. So what we have here is the respirometry apparatus that we're using to capture the hummingbird's breath and measure its metabolic rate at the same time. So when the hummingbird flies up to this little tube here, he has to stick his head inside the tube in order to reach the nectar, which is up there at the back. And when he does so, he's breathing in and out quite rapidly, all while he's hovering and feeding. And as a result, he's exhaling CO2 and consuming the oxygen in the air. All the while, we're sucking air through this tube, so in through the mask, past the hummingbird's head, and onto our respirometry equipment, which measures the level of oxygen and the level of carbon dioxide in that airline. So we can see the oxygen that's missing, that the hummingbird has been consuming, and see the extra CO2 that the hummingbird has added. And in this way, we can measure the metabolic rate. If we then capture into a tube some of that exhaled CO2, we can send that off for analysis and detect that special isotopic ratio, that carbon signature that we're looking for in that exhaled CO2. We offered fasted hummingbirds a labeled sucrose or table sugar solution. When hummingbirds first fed on this solution, the respiratory quotient, or the ratio of carbon dioxide produced to oxygen consumed, was near 0.7, indicating that the birds were primarily oxidizing lipids. Very quickly, though, as hummingbirds fed more and more, the respiratory quotient moved closer to 1, indicating that the birds were now burning almost exclusively carbohydrates. Throughout the rest of the experiment, this RQ remained near 1. However, this doesn't tell us from where that carbon is originating. During that same first feeding following the fast, we determined that the hummingbird was relying exclusively on onboard carbon stores, stored fat. And as the hummingbird ate more and more, as the RQ rose towards 1, we saw that the stable isotopic signature rose such that it was indicating that the bird was now burning exclusively dietary carbon, the sugar that it had been eating. When we then removed the labeled solution of sugar and replaced it with one with a signature very near the maintenance diet that the hummingbirds were used to, that stable isotopic signature immediately dropped down such that it reflected the newest unlabeled carbon source. So hummingbirds were still burning carbohydrate, and it was the newest sugar that they had been eating only. Then, instead of offering hummingbirds a sucrose solution, we offered them a solution containing just glucose. Remarkably, we found that the pattern was just the same. Hummingbirds could rely exclusively on newly ingested glucose to fuel their hovering behavior. Then we tried with a fructose solution, and remarkably, the results were just the same. Hummingbirds didn't care what we gave them to eat, glucose or fructose or sucrose. In each case, they burned only the newest, most recently ingested sugar. Overall, our research shows that hummingbirds' behavior and physiology are both finely tuned so that they can make optimal use of the energy in their sugary diet. Going forward, we want to understand exactly what molecular mechanisms and adaptations allow hummingbirds to move that energy through their bodies as rapidly as they do. In addition, we want to understand if both behavior and physiology change across seasons in ways that allow hummingbirds to store fat at as fast a rate as they can in advance of a migratory journey.